Hello everyone, I'm Hossein Rajabi Faqihi, and today I will be talking about our paper titled Is Semantic Parsing Effective in Procedural Reasoning? This is a joint work with Parisa Jamshidi, Choman Tang, and James Allen, and is done in Michigan State University with our collaborators from Florida Institute for Human and Machine Cognition. Let's get right to it. What is the problem that we're addressing and what is the task? Let's assume a procedural text where we do have a process which describes a series of actions which essentially change the status of the word from one point to another. This process can be split into a set of steps, and through these steps and actions involved in the steps, the words around the process would be affected and altered in terms of entities and the status of those entities. We can assume a recipe to be a process. The entities are essentially like ingredients or the final outputs of the recipe. Procedural reasoning is basically to reason about the process in terms of its effect on the word. And remember, like the process actually affects the word through a set of actions, and each action has a set of consequences which would alter the state of a set of entities. The task that specifically we are trying to solve in terms of procedural reasoning here is entity tracking, which is proposed in this data set called PROPOLIS, where we do have a set of paragraphs. For instance, roots absorb water from soil, the water flows to the leaf. And then there are a set of interested entities as called here participants, which were interested to know their location at each step. For instance, water after roots absorb water from soil is at roots, but mixture and trigger does not exist, and we don't know where CO2 is. Now that you know the task and the problem, let's see what is our intuition for including semantic parsers in this setting. First, we want to do reasoning over both local and global context. For instance, let's assume this scenario where step 1 says magma rises to the surface and step 2 says magma cools down to form lava. From the semantic phrase of the second sentence, we do have this. The predicate is form, the affected is magma, and the result of that frame is lava. So in order to understand what is the location of lava at second step, we have to do this chain of reasoning. First is the location of magma at step 1 is surface. Second, we know from the semantic frame that magma is the consumed object in making lava. From common sense, we can have this that in a conversion, the location of the result matches the location of the consumed object, and hence we can conclude that the location of lava is also surface. Another use case is this, basically common sense through ontological features. For instance, if you assume this other step that says generator makes electricity, from the semantic frame we have the predicate make, the agent of that predicate is generator, and the result is electricity. So if we do the chain of reasoning, the common sense tells us that agent and results are usually co-located, and also the result can be inside even the agent, especially if the agent is a container. And from ontology features, we do have the generator is a container. From the semantic frame, we had that the agent of that make is generator, so we can conclude that the location of electricity should be the generator. Okay. So now that you know our intuition on the task, how do we get this semantic parses? What is the source of this information? How do we represent them? We use two different sources for the semantic parsings. One is a shallow parser that is a deep neural net model trained with data for semantic role labeling, and the other one is a symbolic deep semantic parser called TRIPS, which works based on ontologies. We basically represent each graph, each sentence based on a graph where different phrases are connected to each other based on the semantic relations that we can extract from the parser. And to connect different graphs to each other for each local sentence, we rely on an exact match of entities and candidate locations and coreferences, essentially like the same span being repeated in two different sentences, or like a pronoun being referred to another sentence. Let's assume that this sentence, like move the book on the shelf to the library, the Israel graph is giving us the move as a predicate and then two arguments of that move. The trips graph gives us a much more fine-grained information, which we actually see that move is connected to cause move. There is an agent U, which actually is not even in the sentence, but it can be extracted. There is an affected book, and we know its grounding to be on the shelf. And the result of that move is another grounding to the library, which we know the library is a container and can actually contain book. We know that also book is non-self-moving. So you can assume, given all this fine-grained information, we probably can even do reasoning over the process, the entity like evolutions and the state changes, their location, without even like a specific data for procedural reasoning, right? We could just use these graphs and then interpret those in terms of what is happening to the entities. And this is specifically what we're doing here, and we call it symbolic procedural reasoning because it doesn't use the data and it doesn't use any neural learning. We call this method PROPOLIS. PROPOLIS essentially builds up over the TRIPS parser to help us directly predict the actions and locations of entities inside the process, and consists of 3 modules. The first module is a graph abstraction. Graph abstraction maps the graph to a set of actions of move, destroy, and create. And for each of these mapping and frames, it also selects the important rules, for instance, agent, affected, result, and so forth. It basically gives us a generalization over different verbs. For instance, put, move, and place all are mapped to move, or form and create are mapped to create, right? Let's see an example. This sentence says, clouds from the sky collide in order to create water droplets. And you can see here, there is a move event. Its affected is actually clouds from the sky. The same, like span is also the agent of the next event, which is create, and a create affected result is water droplets. So this is the basically graph that we have mapped and abstracted from a very large graph of trips. After getting this abstracted graphs for each sentence, we do have a rule-based local decision-making process, which essentially relies on a set of hand-designed rules to extract the actions happening to each of these entities involved in these abstracted graphs. For instance, if I have a move event as a main predicate, and the rules connected to that move event are affected and agent, the one that is connected as an affected is the one that is being moved. Or for instance, if I have the same move event, but I only have agents, the agent is the one that is being moved. This is not an indefinite set. It's basically a finite set of rules that we can define because the input graph is actually has a finite set of structures. After we draw all these local conclusions or decisions about the entities, we have to make sure that they are consistent from each other throughout the process. So for instance, if our initial prediction for step 1 was move, step 2 was create, and step 3 is exist, this is not possible. This is what we call action consistency, and we apply a rule that changed the initial prediction to move, exist, and exist. Additionally, there should be also a consistency between locations and actions. For instance, if you predicted the location of the entity on step 1 to be location 1, and on step 2 to be location 2, but you didn't predict any move action, this is not possible. So you either have to predict move from location 1 to location 2, or you have to say there was no move, there was only location 1 and location 1. This is the symbolic process, but can we go beyond and do neurosymbolic, essentially use all the information that we got from the parsers, and also learn from the data at the same time with the help of the neural models? We examine this by 2 different neural backbones. The first one is NSET, which essentially encodes the sentence and then uses the explicit mentions of the entities that it can find through the sentence, extracts the representation of those, passes that to an LSTM and a serif layer to get the action that is happening on the entity, and also concats that with the location candidates and extract the location of each entity at each step. The other one is TSLM, which is basically a more global model, where we ask this simple question of where is the entity, and then the whole context is used at each step. But how do we define like which step we are asking the question if you're including all the context? The trick is that they have introduced basically a timestamp encoding, which specifies which step we are focusing on when answering a specific question. For instance, when we are at step 1, we show that the trash is made in the house, and that's like getting an additional representation showing this is a step of our focus, and the rest are future. If we go to step 2, the focus shifts and so forth until the last step. Then the span of the answer, we extract like basically a span from the context to be the answer to the location, and also the CLS tokens are used in the same serif like layer to extract the action. Okay. So to do the integration, we rely on a graph attention network, which basically is used to encode the semantic graphs that we have. So essentially, once we have the graph of the connections between different words and phrases from the semantic parsers, we get the initial representations from the backbone architectures, and then pass that to the graph, do a couple of layers of message passing, and get an updated representation. Then we update the representations based on these updated representations and the original representations by concatenating the two with each other. For the CGLI method, we also use the question node to also inform the context of what we are basically asking for. Okay, So how do we evaluate this model, and what are the sets of experiments? We are using two prior evaluations that exist for this task. The first one is sentence level, and has three different categories. In category 1, it evaluates whether an entity has been created, destroyed, or moved. Category 2 evaluates when the entity was created, destroyed, and moved. And category 3 inquires of the location of the creation, destroy, and movement. For the document level, we basically evaluate based on F1 measures on the accuracy of the model for detecting inputs, outputs, conversions, and moves. And you can assume that these are actually not the direct decisions of the model, but can be concluded from those decisions. In terms of the performance, if you look at here, so PROPOLIS is basically performing better than a lot of like at least 3 neural models that we have listed in this paper, and it is not using any data, but we know that this is limited in terms of what it can do, because it's not prone to noisy information, and it also cannot generalize much over just the initial set of rules that we have defined, and it's of course a limitation to a rule-based system. However, we see here that if we integrate those graphs with the integrated method that we proposed, the results go from 66 to like 69.9 when we integrate the NSET model with PROPOLIS, and all of these integrations have the improvement that we want. However, once we integrate this with the CGLI method, the CGLI plus TRIPS actually fails to improve the performance based on these two metrics. Although this is not the end of the story. We propose an additional evaluation metric which directly evaluates the model based on the decisions that it makes, basically the low-level decisions. And we categorize a set of decisions into their level of difficulty. And we have these categories. First is a local decision, which both entity and location exist in the current basically sentence. The other one is global location, where the location does not exist in the local sentence, but the entity does. Global entity is where the entity doesn't exist in the local sentence, but the location does. And global decision is where neither exists in the local sentence. We have another category called locally ambiguous sentences, where we do have multiple actions happening in the same sentence, and we do have multiple entities, and we want to know which entity is affected by which action. This is the performance of the model. So if you compare the NSET model with the other integrations of semantic parsers, you can see that consistently all of the metrics are actually improved. And you can see that the improvement in the global cases are higher, even though the original NSET model was not really good at that, and it keeps like a little bit of improvement over the local decisions as well. Once we move to CGLI, compared to CGLI plus TRIPS, remember that we didn't see any improvement in the prior metrics, but here we clearly see a large amount of improvement. And you can see, like, the CGLI method was a global method, right? So it was already good at deciding about global information. And we see here that the local information have seen much more of a boost. So we can conclude that basically the integration process has a complementary effect or a complementary improvement to the capabilities of the original backbone. Okay, so we conclude that we have proposed a new evaluation metric, which kind of like evaluates the model on the low-level decisions and clarifies really how good the model is performing. It also showed us that the hardest decision is where the entity and location actually do not appear in the local context, while the decisions over global entities is even harder than the global location decisions. We also showed that the symbolic procedural reasoning outperforms many neural models, especially when pre-trained language models are not used. And also the integration with a state-of-the-art neural models are really helpful in most of the metrics, and the integration has a complementary effect on the original backbone. Thank you for listening. If you have any additional questions, please don't hesitate to contact us at rajabfa@msu.edu.